So today we'll discuss some other aspects of organic reactions like cyclization and ring opening. Right. So see, till now whatever we have discussed in addition or substitution reactions or even elimination reactions, they can be either categorized in polar reactions, right? So due to the bond polarity some nucleophilic attack is there, or they can be thus radical type of reactions we have seen, right? Like Kharash peroxide effect, that was a radical reactions. Now see this example of where 1,3,5-hexatriene is converted into 1,3-cyclohexadiene. That means one of the double bond, pi bond, is vanished and a new sigma bond is formed, right? Now this type of reaction where there is no external reagents, any other reagents, only either heat or in some cases we will see that there is light involved, right? So only heat or light is there without any external reagents. The electrons of the reactants just reorganizes to form the product. This type of reactions are called pericyclic reactions, right? And see this, the first example here is a cyclization, so it is cyclization, and the second example where cyclobutene is converted to 1,3-butadiene, this is a example of ring opening, right? And of course these are reversible reactions, so you can also convert cyclohexadiene to this one, though of course the you can see the size of the arrows, right? This suggests that in which side the equilibrium will be favored. Okay, and in this example, though this is not a cyclization reaction or ring opening, these are Diels-Alder reaction, also another class of pericyclic reactions, right? These are cycloaddition reactions. We will also discuss this in very little at the end, right? Now to start with, we have to see that these reactions are all symmetry allowed. What is symmetry allowed reactions? We'll just look into it in the next few slides. And all these reactions are governed by Woodward-Hoffmann rules, right? What are Woodward-Hoffmann rules? We'll slowly we'll slowly get to that. And for these rules, Woodward and Hoffmann received the Nobel Prize also. Right. Now this symmetry of these molecular orbitals are very important for these reactions, right? See, if you just remember what we learned during module 1, right, during molecular orbital theories of the pi systems. See, for a 1,3-butadiene, so this is for 1,3-butadiene. This is a 4-pi electron system, right? So for 4-pi electron system you will have 4 types of pi molecular orbitals, and which looks like this. The red and the blue just suggest opposite phases, right? And the 4-pi electrons will be arranged in this way as per Hund's rule, right? And the HOMO is the second one and the LUMO is the third one, and we are considering for these pericyclic reactions only the HOMO and the LUMO, right? These are very important to us. Now if you see the symmetry of this 1,3-butadiene, this 4-pi electron system, what do you find? They have alternate type of symmetries, right? See, psi 1 and psi 3, this is psi 1 and this psi 3, they are symmetric. Symmetric means you can draw a line of symmetry between them, right? See, the both halves as if they are mirror images. Whereas psi 2 and psi 4, they are not symmetric, right? These we have to bear in mind. We'll need it further also in next discussion. So what we saw that in 4-pi system the HOMO is not symmetric. This is important, right? So for 4 pi electron system, this HOMO, that is the Psi2, is not symmetric. Now in pericyclic reaction we will only consider these HOMOs, right, where the electron is there in the highest occupied molecular orbital. Okay, now see, in this panel it is just drawn in this fashion, right? The same molecular orbital is drawn like this, right? If you see the lobes here, right, they are they are not in the same phase, right? Now to form bond, what we know, that the lobes have to that will overlap, has to be in same phase. To do so, this one if you rotate in this direction, and this one if you rotate in the same direction, right? So both are rotated in the same direction. In this case, say if you rotate it anti-clockwise, both of them, right? So we end up in this cyclobutene type of structure, right? So this is this new sigma bond is formed, and the pi bonds are opened. One of the pi bond is rearranged, vanishes, and other pi bond is rearranged. Right. So this type of rotation, where both the orbitals are rotated in same way, is called conrotatory, right? You have to remember it. This is called conrotatory. Now this conrotation, right, if you reverse it, that means now you are trying to ring open it. See, that means you want to get to 1,3-butadiene, and which is the HOMO of 1,2-butadiene? This is the HOMO, right? Now to get to this HOMO, again if you want to open this bond, again you have to rotate it in the same way, right? Here in this case you are rotating it clockwise. Both of them should be rotated clockwise, otherwise you cannot get here, right? That means this is also conrotation. And what is the condition of the reaction? This is thermal reaction. That means just by application of heat. Okay. So for 4 pi system, in thermal condition, what we see? We see that conrotation. Conrotation means the rotation of the orbitals in the same direction will give rise to this ring opening and cyclization, both. Now let us see the next the implication of this conrotation on the stereochemistry of the products, right? See, now we saw that this is the only way, right? In thermal condition, conrotation is the only way to form the product. See, for simple 1,3-butadiene it's not a problem because no isomer is possible. But if you have substitution in the terminal this kind of terminal carbons, right? See, this is again the framework is same. This is a 4 pi electron system, so the framework will be same. It will behave similar way. But if you draw it, this one, say this is CH3, this is H, this is CH3, this is H. Okay, so I have drawn it here like this. Okay, so this is what? This is 2E4Z hexadiene, right? 2E4Z. See, this is in the 2 position you have a trans type of configuration, so it is 2E and here it is Z. Okay, so if you start with this isomer 2E4Z hexadiene, right, and you have only one way to do the reaction, that is conrotation. If you do it like this, then what you will have? You will have this methyl up here, hydrogen down under, right? Similarly, the methyl here also will go up because you are rotating in the same direction, and hydrogen will be under, right? As such, this will be the cis 3,4 dimethyl cyclobutene, right? You cannot get the trans one by from here, from this EZ hexadiene system, because there is only one way, conrotation, right? You cannot get see this trans 3-methyl dimethyl cyclobutene from EZ, that is 2E4Z hexadiene. Right. Now see what will be the case if it is both are E, that means 2E 4E hexadiene. See, in this case, if you do the con rotation, now this methyl will be here, right? So when the methyl is here and hydrogen will be here, now in this case, right? That means what? Now you will get the trans product. Now if you want to get trans 3,4 dimethyl cyclobutene, what you have to start with? You cannot start with EZ hexadiene. You have to start with 2E 4E hexadiene only, right? In thermal condition. Again, you have to mention the condition, right? This is also important. Right? So under thermal conditions, if you want to get the trans cyclobutadiene, dimethyl cyclobutadiene, then you have to start with EE hexadiene. Whereas if you want to get cis, you have to start with EZ. So that means one particular stereoisomer, right? These are two stereoisomers. One particular stereoisomers will give only one particular stereoisomer of the product, right? This kind of reactions are again called what? Stereospecific reactions. Okay. Now let's see this 135 hexatriene system, that means 6 pi electron system, right? 6 pi electron system. Here, you know, as we learned in module 1, we can draw the molecular orbital as shown here, right? Now see which is the HOMO. Here this is the HOMO. Now interestingly, in 1,3-butadiene case, 4 pi electron system, the HOMO was not symmetric. But here the HOMO is symmetric. See, the HOMO here is symmetric. Now if we draw it like this, right? Now to form sigma bond, can you rotate them in the same way and form it? Now you cannot rotate this in the same way. You have to rotate it in opposite directions, right? To form this bond, overlap bond. This kind of rotation is called disrotatory. That means you are rotating them in opposite direction. Now this rotation is the only way in thermal conditions to form bond, sigma bond, right? For 6 pi electron system, which was con rotation in case of 4 pi electron system. Now see, this has just the opposite implication in case of stereochemistry. Right? Now if you start with EZ, right? If you start with EZ, in cyclobutadiene case, what happened? We started with EZ and we ended up in cis. See, in this case, opposite will happen. You start with EZ in the terminal carbons, of course, this doesn't matter, right? In the middle one. So you start with EZ and you end up with trans, right? Similarly, in the cyclobutene case, when you started with 2E 4E hexadiene, you ended up with trans. But here you start with 2E 6E, right? And you end up with cis. This has, because see, they are solid bonds, that means both the methyls are towards you, so in the same direction, so they are cis. So in the same thermal condition, 4 pi and 6 pi will behave differently. That why? Because the homos, the symmetry of the HOMO is different, and we mentioned already that these reactions are symmetry allowed only, right? If the symmetry allows, only then the reaction will occur, right? So 4 pi and 6 pi system behave differently, right? As you saw here. Now the most interesting part is these photochemical reactions, right, with light. Now we started with the same thing. This is again the 4 pi electron system, right? Now if you subject it to photochemical photo irradiation, light irradiation, then one of the electron from the HOMO will jump, from the psi2 will jump to psi3. That means in photochemical condition, psi3 is the HOMO, right? Psi3 is the HOMO. And see, now the HOMO is symmetrical. That means what? Con rotation will not give product. Now dis rotation will give product. That means disrotation gives products means the stereochemistry will be just opposite of the thermal conditions, and that is what we get. In thermal condition, Ez gave us cis product, but in photochemical condition, Ez will give us trans product, and just the opposite. That means EE gave us trans product in thermal condition, but in photochemical condition, EE will give us now cis product. Right? With a bit of practice, we can master these things. So no need to memorize it. Just a bit of practice is enough, right? If you draw the same thing side by side, it will be much more clear to you. Okay, so photochemical reactions will have just opposite stereochemistry to that of what? That of thermal reaction. And why it is so? That is because of this change in symmetry of the HOMO, right? So from asymmetric HOMO in thermal condition we have a symmetric HOMO in photochemical condition for 4 pi system, and for 6 pi system it will just be the opposite. That means from a symmetric HOMO, right? For 6 pi system, this was symmetric. From symmetric, that means from disrotation, now we'll end up with a conrotation, because this is at asymmetric, right? Now you have to rotate this in same direction to form the bond, and of course this will result in just the opposite stereochemistry that was found for thermal reactions. Okay, now you see you have both the E's in thermal reaction produce cis, right? Here we have a trans compound, whereas just the opposite is occurring for the other isomer. So these reactions are called stereo-specific reactions. Okay, so to summarize electrocyclic cyclization, right, we see that only the symmetry of the HOMO is important, right? For thermal case, what is the HOMO we have to consider, and for photochemical case, what is the HOMO we have to consider. And actually, if you first we have to draw all the pi orbitals, and for photochemical we have to just promote one of the electrons in the HOMO to the next higher level, which becomes the HOMO in photochemical condition. So the symmetry is just altered, just opposite that of the HOMO in thermal conditions, right? So after you have assigned the HOMO, right, if it is a symmetric HOMO, then you have to remember this disrotation. That means from opposite direction rotation will give the bond. If it is asymmetric HOMO, then conrotation will give the product, right? Now this is symmetry allowed pathway in which the phase orbitals will overlap, right? And the reaction will be forbidden, right, if it is not symmetry allowed, right? If it is symmetry forbidden, then it will not take place in this concerted pathway. Concerted means in the same time these bonds, the electrons reorganizes, the pi bond breaks and the other pi bond shifts and the sigma bond forms in the same time. That's why they are called concerted pathway, right? And the symmetry of the HOMO of the compound undergoing ring closure controls the stereochemical outcome of the electrocyclic reaction, right? So the HOMO of the compound is very important in this electrocyclic cyclization. Now you can summarize the Woodward-Hoffmann rules for electrocyclic reactions, right? These are the Woodward-Hoffmann rules in tabulated form for electrocyclic cyclization as well as ring opening. So suppose if it is 4n pi electron system, that means our 1,3-butadiene 4 pi electron system, right, where n is 1, 2, 3, 4, right? So if it is so, see, then in thermal condition the HOMO will be asymmetric and conrotation will give the product, right? And the photochemical, the HOMO will be symmetric and disrotation will give the product. And for 4n per 2 pi system, that is our say example of this 6 pi system, just the opposite will happen. Now the thermal condition will give disrotation and photochemical condition will give conrotation as the product. So with this we can end our discussion on electrocyclic cyclization and ring opening. But before ending this lecture, I will just like to mention another pericyclic reaction that I have already mentioned in the first slide, these cycloaddition reactions, right? And we cannot say that these are pure ring opening or ring closure reaction, but I thought that these are worth mentioning when we are discussing electrocyclic cyclizations. See, if you see this example, this is the 1,3-butadiene, right? So this is a 4-pi electron system, whereas this is the ethylene, right? That is a 2-pi electron system. That's why above the arrow it's written 4 plus 2. This in the third bracket it is called 4 plus 2 cycloaddition reactions. And what they form? They form hexene and cyclohexene, right? That means just by rearranging these bonds, right, these electrons between these two reactants, we get the product without any other reagents, right? Here also, see, if you want to donate electron, you have to donate it from HOMO. If you want to accept electron, you have to accept it in LUMO, right? So in the first picture you see here, it's the HOMO of the diene and the LUMO of the dienophile. Why it is called dienophile? Because it is likes the diene. That's why it is called dienophile. As in nucleophile, electrophile, we say this is the dienophile, right? So here we have shown the HOMO of the diene and the LUMO of the dienophile, right? Now if you draw it like this, these are matches, right? So they can overlap, they are on the same phase, they can overlap and form bonds. But if you take the other way, that means if you take the LUMO of the diene and HOMO of the dienophile, then also you can form these overlaps, right? So you can take either. Just you have to remember that in this case of cycloaddition reactions, you have to consider HOMO of one and LUMO of the other, right? Now as you see that this is the only way, right? You have to overlap. Here also this is also stereospecific reactions, right? So if you have substituents here, different kind of substituents, so they will give rise to different isomers of the product. Okay, now more important or very interesting is this thing, the 2 plus 2 cycloaddition reaction. That means a 2-pi and another 2-pi system. Here you see an alkene, the ethene, right? These are two ethene systems, right? So in thermal condition there is no reaction, whereas in photochemical they can form the cyclobutene. Why this reaction does not take place in thermal reaction? You can just explain it by following the HOMO and LUMO of these two species, right? Now if you draw for one of the ethene, if you take the HOMO of it, it looks like this, right? They are in the same phase, these green lobes. Whereas if you take the LUMO of the other molecule, it will look like this. See, there is no matching, so no overlap takes place in thermal condition. Whereas in photochemical condition, the LUMO of one is fine, you have to, this is okay, right? It is same as this one, but now the HOMO of the other molecule has also changed its symmetry, right? This is not the HOMO of the thermal condition, right? Now because the electron has promoted to the higher orbital. Okay, now they are of same symmetry, right? So they can overlap easily, right, and form bond. So this explains why this this cyclization reaction does not take place in thermal condition but takes place in photochemical conditions. Okay, so we can end our discussion regarding these pericyclic reactions and ring opening and cyclization reactions here. There are another major class of pericyclic reaction, that is sigmatropic reactions, but we'll restrain ourselves from discussing that reaction in today in this lecture.